All right, so this screencast, I am trying to let's say that I was thinking about doing some cities, but I ended up doing small distances. So we've got like a blue spot there and a blue spot there. We got a lens here at a certain d distance away. The width of the lens is or the length what did I say? 0.04 meters. And then our focal distance is zero point 0.4 is zero point 0.4 meters. And we're looking for rho. So I get some really nasty numbers. So how far is rho? That's the distance between spots on the screen once it's gone through the lens. So here we go. So we've got this equation here that I was using, and so first there's a certain angle, a critical angle, which we've got to inequality, which is k. That is actually that's 2 pi over wavelength, and I'm saying the wavelength in this case is 2 times 10 to the negative sixth times L. That's the length of the mirror times rho over 2f. And what we're and what that's going to tell us is so literally, and then we need the angle of separation there to be about 1.22 pi to be to be visible. That's apparently the minimum angle. So anyway, using those data values, I plugged those into the equation, and I ended up with a value with our constraints of 2.4 times 10 to the negative 1, 2, 3, 4 times 10 to the negative 5, and that is the distance the spots would be on here. So here we're 2 meters, and now they're really close together. So clearly this mirror is a converging mirror. Clearly. So anyway, we've got that going on. And then to determine this distance d, so there's a ratio here where well, the ratio is d over f equals r over p. So to solve for d equals fr. F is the focal length there, and d obviously is that distance, and then or not p, rho, and comparing those, and we get a distance to make this true in this crazy situation of like 32,000 meters. So that's how far apart we've got to be in this lens contraption. So very tiny rho and a very big D. So that is my submission for resolution. All right, so this screencast is the one I just talked to you about. You might be hearing me making it. I don't know. Depends how good your ears are. But anyway, so this is the Gratings one, and I used equation number. Is there even a number in it? No, it's an equation on page 284, on the top of the page. There's no number. But as you know, actually, that is not the equation I just used. Equation number 1127 is what I used. And as you know, I know how to derive it because I just know, and I don't need to tell you about that because you know I know. So anyway, so that equation is trying to, it's saying, it's comparing the intensity at the peak intensity of the grating. So in a grating, let me just talk about that for a second. Okay, so literally it's like a grate, like a what you would see in a vent for a heater, but so there's these little holes that that light goes through, and then there's these little then then this part light cannot pass through. And then what that does is when the light goes through the grating, then the light will create an interesting pattern on a screen that's far away. So you have grating here, and then down here you've got the screen, and light can spread out or can diffuse diffract, whatever. So anyway, so we're moving light along there, and so the distance between each of the grates, that's our delta x, and then our distance between that and oopsie. There we go. Between the full distance between of the from the grate border to the end of the clear space. There should be a name for that. It's actually H. So anyway, but wherever the maximum intensity here within the individual grading, that's what we're looking at, and that's what that I. So that's what how the peak is, and then we have an equation then for various values of x, which is on the screen, and then z, the distance away. So I throw that equation in. I'm using a dx of 10 to the negative 7, so a very fine grading. Wavelength 5 times 10 to the negative 6. And then z is 10, so we're going 10 meters. H is a little bit bigger than dx, 1.5 times 10 to the negative 7th, and then n, which is 5. I plotted that, and then this is what the plot I got. So at 0, we're getting 100% intensity of the light, and now this is for our x value. So if we as we so if our which so compared to our original, if x is 0, we get 100% intensity. However, as we move our x, we start to go down. Now here is x at 10, which makes sense because we're at a greater angle. We're at a further angle from the original source of the light, so we're losing some intensity, not a ton. I mean, we're only down to 93% here after as of 10. Well, let's say we move our let's expand x out to 100 to see what happens. I'd bet you we're going to lose most of all of our light. Oh yeah, we do. Yeah, here at about 60 we lose, but this bump is kind of interesting. Why all of a sudden we bounce back up just ever so slightly. So anyway, that is an example of how to do a grating problem.